Okay, this is a screencast to walk you through using R to create some visualizations that we did in class, looking at bimodality in Finchbeaks and looking at the way that Finchbeak width, length, and depth are all correlated with one another. These files are all on the Moodle site, so if you go to Moodle, you go to the Evolution and Ecology section. I'm logged in as a student. If you scroll down to this week's material, which is September 16th to 22nd, you see that there's a bimodal Finchbeaks R script, a bimodal Finchbeaks data file, a Finchbeaks 3D scatterplot R script, and a Finchbeaks data file. The bimodal Finchbeaks data file is a reduced data file that only includes El Garapatero data from a year in which El Garapatero was bimodal, and so it will allow you to see the bimodality. The Finchbeaks data is a full data set of a lot of different finches to show you the correlation between length, width, and depth that we use to make the three-dimensional rotatable scatter plot that we use in class. What you need to do is you need to download all of these, and then once you've downloaded them, you need to go to your downloads folder, and after you've found them in your downloads folder, if you right-click on it, if you have a Mac, and open downloads, your most recent files will be at the top, more than likely. And once you've downloaded it, you need to then put it in a folder altogether. Put all of the data files and all of the R scripts in a folder together. I have stored mine in my Dropbox folder so that Dr. Judd can have access to it in the Bio133 materials directory and in the Finchbeaks R script. So here you see bimodal Finches R script, Finchbeak R script, bimodal Finchbeaks data file, and Finchbeaks data file. Having them all in the same directory or folder, we now use the terms folder, but back in the old days they were called directories. It's just places in your computer's memory where you store things. So in this folder, the R scripts are in the same place where the data are, and it just makes things a little easier. So what you want to do is, if you've got R installed on your computer, so I can go to Applications and I can check and see that RStudio is installed, and I can also see that base R is installed. If you have base R in RStudio, you can just click on RStudio and it will open up. But what I want you to do is I want you to open the bimodal Finches R script. And when you do, it will open up the RStudio window, and I'm going to make my window as big as my computer is so that you can see things easily. And in the R environment, it has a number of different things, a number of different windows. One window shows your R script. Another window down here shows your R script as it's being executed. Up here is an environment tab where you can look at history and connections to outside things. So if you're going to go get something at GitHub, it'll show those connections. It shows my history. You can see that I've been playing around with the Finchbeaks data. You can clear this history out if you want, so that you start with a clean slate. But over here in the upper left-hand corner is where you want to do things. And all of my R scripts that I write for you guys to use will have annotations that tell you how to do things. So the first thing that you want to do is you want to make sure you're in the correct directory. So getwd just is shorthand for get working directory, and you're asking it to tell you what working directory you're currently working out of. And it should have the working directory down here. That is the working directory where all of your scripts are and all of your data are. So you can see that this is in the Finchbeaks data and R scripts file, a folder within the Bio133 materials within Dropbox on my computer, and I'm the user. So we need some packages. ggplot2 makes plots. rmisc does a ton of things. It's basically miscellaneous R stuff. And car is another package that you might need in the process of doing this, because you have to calculate things about the distribution. So the first thing that you want to do is you want to import the data file. So what this line of code right here basically does is it essentially says, I want you to make a new thing called beaks. And this thing here, which is the lesser than sign and a dash, basically says, I want you to do the thing to the right of that. And when you do that, I want you to make something new and call it beaks. So what I'm asking it to do is to read a CSV file. CSV stands for comma separated values. Comma separated values file, so it's just a data file where it's the value that's separated from one another with commas. And the CSV file that I want you to read in is called bimodal Finchbeaks. It's a reduced data file that just has one population's data in it, El Garapatero's data. So what this essentially says is I want you to read a CSV file. The CSV file that I want you to read in is bimodal Finchbeaks, and I want you to store it as beaks. In this way, I don't have to keep writing bimodal Finchbeaks over and over again. Whenever I want access to this file, all I have to do is type in beaks. So when we do that, it will show that you've done it down here. And to look at it, you can type in head. And head basically means I'm going to give you the first 6 lines of whatever is in the parentheses. So I'm going to get the head of beaks. And what it should show me is the first 6 lines of the file, which are beak lengths of a bunch of finches. And so then I want to make a histogram. And histograms are pretty easy to make. This is a ggplot block here, where I'm basically saying, I want you to make a plot. The data I want you to use is beaks. The thing that I want you to plot is mean beak length. I want you to make a histogram that has a certain density to the bars. It's going to use Y is density, telling you what the frequency is. Position is identity. I actually don't know what that means. And then I'm telling it how wide I want it to make the bins. And I want it to be a black and white plot. So when you run this block all at once, it gives you a plot that shows you over here in the right-hand corner a frequency histogram of beak length and how frequently different beak lengths occur. You can go over here and make this bin width smaller and run it again, and it's just going to divide it up into finer and finer scales, but you can still see the bimodality. So you can change bin width to be whatever you want and just rerun it to make whatever pretty picture you want. But then the other thing that they do in the Hendry et al. Paper is they do what we call QQ plots. And a QQ plot is just a plot that shows you what the cumulative frequency distribution is of an observed data set versus what the cumulative frequency distribution would be of a theoretical one. And we want to compare our actual data on Finchbeaks with an expected normal distribution. And so what we can do here, what QQ norm does is it's making a QQ plot of the mean beak length. And as you can see down here, this has a S shape to it, a slight S shape to it, because this is actually the observed data, and then we can plot the line of what we would expect if there is a normal data set. And what we see is that as you increase across the distribution, and the distribution, remember, before was this distribution, as you start gathering data, what it's showing you is that in a bimodal plot, early on in the distribution, so imagine that this was a normal distribution, the peak would be somewhere here in the middle, but early on we start gathering more and more data early on so that our cumulative frequency distribution gains more observations early on, more than you would expect if it was a normal distribution. Then, as you kind of get into the middle part, you start gathering fewer observations in the cumulative frequency distribution. And then as you get out to the tail, you get more once again, as you get to that second peak. And then when you get out to the edge of the distribution, you're gathering fewer because you've already gathered up all of the observations. So a normal distribution would be right along this line. A bimodal distribution has this S-shaped, where early at the left side of the bimodal graph, you're gathering more density than you would expect if it was normal. In the middle, you're gathering less than you would expect, and on the other end, you're gathering more than you would expect. So this is what a QQ plot does for you, and you see that these look similar to the QQ plots that are in the Hendry et al. Paper. Now, if you close RStudio, just go up here and quit RStudio. You don't have to save anything because all of this stuff is saved. You can go back to wherever you have your R scripts found, and you can open up Finchbeak scatterplot. And so this is the Finchbeak scatterplot code for doing the scatterplot that we showed you in class. Once again, check to see that you're in the right directory. You see that we're still in the Finchbeaks data directory. Download a different file, or upload to a different data file, in this case the Finchbeaks data file, but it's the same syntax. I want you to read in a CSV file, read in the CSV file called Finchbeaks, and I want you to shorthand that thing as Finchbeaks. So now every time I type in Finchbeaks, I mean go get that data file. And so we can get the head of that if we want, just like we did before, to make sure that that the data file read in correctly. And so if we ask for the first 6 lines, we see that it has a lot of data in it. The species, the beak length, the beak depth, the beak width, the head length, width, etc., etc. We're interested in beaks, and so I've renamed those columns in the original file, so it's just easier to work with. We need an RGL, which is a library that does the 3-dimensional scatter plot, among other things. And then we want to attach Finchbeaks because it just will work with the data file a little easier. And then all you have to do to make it do the scatter plot is do the plot 3D, tell it you want it to plot beak length versus beak depth versus beak width, what's the color of the points, and what's the size of the points in the scatter plot. And what you do when you get that is, I made a mistake. I moved something as I was pointing things out to you, so I need to fix that. And when you do it, it will give you a scatter plot, an RGL device. And when you blow the scatter plot up, you see that you have beak length on the x-axis, you have beak depth on the y-axis, and you have beak width on the z-axis. So you can just click anywhere in this, and you can drag this thing around so that you can make it such that you have a plot of beak width versus beak length right there. You can drag it around so that you can see where the most of the variation occurs. So it seems to me like most of the variation is occurring from this corner down here to this corner down here. And so what principal component analysis basically does is it's going to say, okay, what's the maximum amount of variation that we have? And what I want to do is I want to turn this around so that the maximum variation is going from this corner up here to this corner down up there. And then I want to take that box and I want to turn it so that that maximum variation is distributed along a line that basically has a slope of 0. Now I want to take this figure and I want to rotate it around, and you can see that as I rotate it around, there's more variation as you have one rotation than there is in another rotation. There actually looks like there's more variation this way. And so I want to rotate this box so that I have the, if this is the x-axis going from this corner to this corner, the y-axis goes from down here to up here and encompasses the most variation. So that I now have a graph that sends a line through the middle of this data set vertically that spans the most variation vertically, and I want a line that goes through this data set horizontally right through the middle and spans the most variation horizontally. The horizontal axis is principal component 1, the vertical axis is principal component 2, and you'll see that both of these axes go from a positive on this side of that imaginary line that you can imagine going through the middle, and they're negative on this side. If you draw a horizontal line through this data set, values above that line are positive and values below that line are negative. So principal components should always go from some low negative value to some high positive value, and the middle point should be 0, essentially. But it's just a way of taking these three forms of data, beak length, beak width, and beak depth, using their common correlational structure to then create 2 variables out of the 3 variables, and the 2 variables explain the most possible variation that there is to explain in this data set. And that's what principal component analysis does. So these scripts will get you there. I changed this, and I don't want to save any of those changes because I want to make sure that it works for me in the future. So I'm actually, once again, just going to close out of RStudio and not save anything. And that concludes this screencast.